viewers, once again welcome to another edition of Subject Math. Today we will be considering solutions to NECO, WAEC and UTME questions on it. So we'll be solving questions on it, questions from past papers, WAEC, NECO and then JAM, that's UTME. So the first example I have here says, if 53 grams of iron is cooled from 100 degrees C to 20 degrees C, calculate the heat energy lost. Okay, so the first thing we need to do is to write out our parameters. 53 grams of iron. So the mass of iron is equal to 53 grams. Cooled from 100 degrees C to 20 degrees C. So theta 1 is equal to 100 degrees C. Theta 2 is 20 degrees C. So the difference in temperature or change in temperature is going to be theta 2 minus theta 1, which equals to 100 minus 20, and that will give me 80 degrees C, 80 degrees centigrade, or 80 degrees Celsius. So the question says calculate the heat energy lost. So we have to find Q. Calculate the heat energy lost. Already we are given our specific heat capacity of iron to be 4.5 times 10 raised to the power 2. Now take note, the specific heat capacity is in kilogram, joule per kilogram per Kelvin, while the mass is in grams. So we need to convert from gram to kilogram. So to kilogram, we have 53 divided by 1000, and that will give me 0.053 kilogram. Okay? So we go ahead now to calculate the heat energy loss. So that's Q is equal to MC change in theta, change in temperature. Our M from here is 0.053. The C is 4.5 times 10 raised to the power 2. And our theta is 80. So this multiplied by this is 4.5, gives 1908 joules, which can be written as 1.9 times 10 raised to the power 3 joules. So the heat energy lost is equal to 1.9 times 10 raised to the power 3 joules. The second question here says, a block of aluminium of mass M is heated electrically by a 25 watt heater. That 25 watts is the power. If the temperature rises by 10 degrees C, temperature rise, that's the change in temperature, is equal to 10 degrees C in 5 minutes. The time is 5 minutes. Don't forget that we work in seconds. So I'm going to convert 5 minutes to seconds. And that will be 5 times 60, which equals to 300 seconds. So we are asked to calculate the heat capacity of the aluminium. We are asked to find the C of the aluminium, the heat capacity of the aluminium. Okay? So, you recall that PT is equal to MC theta, or MC change in theta. So, P from there is 25. Our T is 300 seconds, which equals to M. We are giving mass as M. Then we have change in theta to be 10. The question asks us to find its capacity, which we don't know. So I'm just going to leave the mass out of it since the mass is m and there's no value for it. So we'll go ahead and make C the subject of formula. So I have C is equal to 25 times 300 over 10. This cancels this. So now I have 750 joules per Kelvin. So the heat capacity of the aluminium is equal to 750 joules per Kelvin. The next question says, water of mass 1.5 kilogram. Water of mass 1.5 kilogram. So the mass of water 1.5 kilogram is heated from 30 degrees C to 80 degrees C. So the change in temperature is 30 degrees C minus, 80 degrees C minus 30 degrees C. And that will give me 50 degrees C, which is the difference in temperature. Using an electric kettle, which is rated 5 amp 230 volts. The 5A, which is 5 amp, it means the current is equal to 5 ampere. Then the voltage is 230 volts. So we are asked to calculate the time taken to reach the final temperature. We are asked to find the T. We don't know the T. So you recall from our formula for calculating specific heat, we have, using electrical method, we have IVT is equal to MC change in theta. So we are looking for the T. We have IV, we have this also. So to make T the subject of formula here, our T is equal to MC change in theta over IV. If you make T the subject of the formula, and then we have T is equal to M, which is the mass. Our mass is given in, this is supposed to be kilogram, joule per kilogram per Kelvin. So our mass is given in kilogram, which is 1.5 kilogram, times the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. The change in temperature is 50. I, which is the current, is 5. The V is 230. And altogether, I'm going to have 273.91 seconds. So the time is 273.91 seconds, which is the same thing as 4.57 minutes. 4.57 minutes. If converted to minutes, our time is this. The first example we will consider is this. A well-lapped copper calorimeter of mass 120 gram contains 70 grams of water. So, the solution. Mass of calorimeter. Mass of calorimeter is equal to 120 gram. 70 grams of mass of water is equal to 70 gram and 10 gram of ice. So mass of ice equals to 10 gram. Both are 0 degrees C. Dry steam at 100 degrees C. The temperature of the steam is 100 degrees C. It's passed until the temperature of the mixture is 40 degrees C. That's the final steady temperature, which is equal to 40 degrees C, the final temperature. So we are given the specific latent heat of fusion of ice, we are given that of vaporization of steam, its capacity of copper, and its specific heat capacity of water. Now, if you observe, the unit of our heat capacities and specific heat capacities are given in joules per gram per Kelvin. So because of that, our mass will be left in grams. We don't have to change to kilograms, so we'll be working in grams. Okay? So if you look at this question very well, it said a calorimeter contains water and ice at 100 degrees C. Then steam was passed into it. So the heat lost by the steam is equal to heat gained by the calorimeter and heat gained by ice and heat gained by the water. So let me analyze the temperatures. So ice at 0 degrees C will melt. Ice will melt. So from 0 degrees C to 0 degrees C. So we have our latent heat of fusion there. Then water. Ice will change to water. The ice block will change to water from 0 degrees to 0 degrees C. Then from 0 degrees C, we are told that the temperature increases to 40 degrees C after passing in steam. So from 0 degrees C to 40 degrees C, there was a change in temperature. This is for the water and this is for the ice. Okay, so for steam already we have 100 degrees. So I'll just go ahead and do my calculations. So steam, before I move on, don't forget that I have asked to calculate the mass of the steam. So that's what we are looking for. It's just going to be ml, which is for steam, is equal to ml of ice plus mc change in theta of water plus mc theta of copper, which is the calorimeter. I want to believe that is clear. According to this statement here, this is what we have. So ml of steam, the heat lost by the steam is equal to heat gained by ice, that's during change of latent heat of fusion, then heat gained by the water and heat gained also by the copper calorimeter. So I'll go ahead and fix in my values. L, which is the specific latent of vaporization of steam, is given as 2.2 times 10 raised to power 3 is equal to M, ice, the mass of ice is given as 10 grams. And the latent heat of fusion of ice is given as 3.2 times 10 raised to the power 2. Plus M of water is given as 70 times the specific heat capacity of water is given as 4.2 times the change in theta. The water changed from 0 degrees C to 40 degrees C after the steam has been passed. So the change in theta is 40 plus the mass of the copper calorimeter, which is 120 grams, times C, specific heat capacity of copper, which is 4 times 10 raised to the power minus 1. The change in temperature is that of water, which is 40. So, I will go ahead and multiply the values. So, M times this will give me 2200 M, which equals to 10 times 3.2 times 10 raised to the power 2 will give me 3200 joules plus 70 times 4.2 times 40 will give me 11,760 joules. And then the last one, which is for copper, that's 120 times 4 times 10 raised to the power minus 1 times 40 will give me 1,920 joules. So by the time I add all of this together, this is what I have. My M is equal to, addition of all this will give me 16,880 divided by 2,200. And that will be equal to 7.67 grams, which is the mass of the steam that we are asked to find. So the mass of the steam is equal to 7.67 grams. I want to believe this is very, very explanatory. The fifth example here says, a piece of copper of mass 30 grams loses 60 joules of heat energy. So the mass of copper is 30. Mass of copper is equal to 30 grams. Loses 60 joules. So the quantity of heat is 60 joules. If the specific heat capacity of copper is 400 joules per kilogram per Kelvin, C is equal to 400 joules per kilogram per Kelvin. So the same should calculate the change in temperature, change in theta. Now, if you observe, you see that our specific heat capacity is given in joules per kilogram, while the mass is given in grams. So that tells you that we need to convert this from grams to kilogram. So 30 grams to kilogram will give us 0.03 kilogram. How did I get that? 30 divided by 1000 will give me 0.03 kilogram. So You recall that Q is equal to MC change in theta. And we are asked to find the change in theta, change in temperature. So let's make this the subject of formula. We have change in theta is equal to Q over MC. Our Q is 60 over M. M is 0.03. The C is specific heat capacity, which is 400. Therefore, our change in temperature is equal to 5. This cancels this. So by the time we multiply and divide, we have 5 Kelvin. So the change in temperature is equal to 5 Kelvin. Change in temperature of the copper is equal to 5 Kelvin. The next question here says 400 grams of cold water is added to 200 grams of water at 70 degrees C. If they are properly mixed and the temperature of the mixture is 30 degrees C, calculate the initial temperature of the cold water. Neglect the heat absorbed by the container. So already I have written out our parameters. So the heat lost by hot water is equal to the heat gained by the cold water. So heat lost by hot water is going to be MC change in theta of hot water equals to MC change in theta of cold water. So the mass of the hot water, mass of the hot water is 200 grams at 70 degrees C. So theta 1 is equal to 70 degrees C. So the mass of the hot water is 200 grams times the specific heat capacity of water. Since we are working in grams, so the specific heat capacity that we'll be using is 4.2. And then the change in temperature of the hot water is going to be theta 1 minus theta 3, which equals to the mass of the cold water, that's 400 times 4.2. Then we have theta 3 minus theta 2. So 200 times 4.2 times theta 1 minus theta 3. Our theta 1 is 70 minus the final temperature, which is 30, is equal to 400 times 4.2. Then theta 3, which is 30 minus theta 2. Theta 2 is what we are calculating. So if we multiply the whole of this, it will give me 33,600. And this will give me 1,680 into bracket 30 minus theta 2. So I have 33,600 is equal to this multiplied by this will give me 50,400 minus 1,680 theta 2. So from here I have 50,400 minus 33,600 is equal to 1680 theta 2. So my theta 2 now is equal to 16,800. This minus this will give me 16,800 divided by 1,680. This cancels this. Here 1, here 1. So my answer is 10 degrees C. So back to the question. The question says calculate the initial temperature of the cold water. So the initial temperature of the cold water is 10 degrees C. Okay, so for this question, they said hot water at a temperature of T is added to twice that amount of water at a temperature of 30 degrees C. If the resulting temperature of the mixture is 50 degrees C, calculate T. So don't forget here they said the temperature of hot water is T, the mass of the water, we assume it is M. So they said it's added to twice that amount of water. That's twice that amount of water at a temperature of 30. The cold water is 2 times the mass of the hot water. So we said cold water here is 2M. And the question asks us to calculate T. So we just go ahead and apply heat loss by hot water is equal to heat gained by the cold water. Heat gained by the cold water. So I have MC change in theta equals to MC change in theta. This is for cold and this is for hot. So for this one, my mass is MC of water. That's the specific heat capacity. I'm just going to put my C. Then the change in theta for the hot water is going to be T minus theta 3, which equals to M mass of the cold water. That's 2M. I'm just going to write my C, specific capacity, as C. Then change in theta here is going to be theta 3 minus theta 2. So I have, from here I have MC T minus theta 3 is equal to 2MC theta 3 minus theta 2. That's 50 minus 30. So I can cancel out the C's. And at the same time, I can cancel out the M. So I have T minus theta 3 is equal to 2 into bracket 50 minus 30, that's 20. So I have T, which is the temperature, minus theta 3 is equal to 40. And I know my theta 3 to be 50. So I have T minus 50 is equal to 40. So T is equal to 40 plus 50, which equals to 90 degrees C. So our T here is equal to 90 degrees C. So from the question above, an iron rod of mass 2 kg and at a temperature of 280 degrees C is dropped into some quantity of water, initially at a temperature of 30 degrees C. If the temperature of the mixture is 70 degrees C, calculate the mass of the water. So here are our parameters. I've written them out. And the heat loss by solid is equal to heat gain by the water. So we go ahead and apply our formula as usual. MC change in theta water. Solid. So my M from here, mass of the solid, which is iron, is 2. The specific heat capacity of iron is 460. The change in theta is theta 1 minus theta 3. That's 280 minus 70. The mass of water we are not given, so that's what we have to find. The specific heat capacity of water is 4,200. The change in temperature, theta 3 minus theta 2. Theta 3 is 70 and theta 2 is 30. So 70 minus 30. 70 minus 30. So I have 2 times 460 times 210 is equals to 4,200 times 40. This is M. So this will give me, multiplication of this will give me 193,200. If I multiply this, I have 168,000 M. So from here, my M is equals to 193,200 over 168,000. And that will be equals to 1.15 kg. So the required mass of the water is equal to 1.15 kilogram. Next question here is a very straightforward question. So I've written out our parameters. We just go ahead and apply this formula for height, waterfalls. So my hem here, we are not given the hem. So I'll strike out the two hems. I will work with C theta and GH. So C theta equals to GH. C here is specific its capacity, and we are given as 4,200. The theta is what we are looking for. Our G is 10 and our H is the 50. So I have 4,200 theta is equal to 500. So from here, my theta is equal to 500 over 4,200. So what I have 0.119 degrees C. So the temperature rise of the water at the bottom of the waterfall is equal to 0.119 degrees C. Our last question. Here are the parameters we are asked to calculate the final steady temperature of the mixture, which is theta 3. So heat lost by solid is equal to heat gained by the calorimeter and water. In this case, heat lost by copper is equal to heat gained by calorimeter and water. So let's calculate the heat lost by the solid. Heat lost by solid. That's MC theta 1 minus theta 3. So we have M, which is the mass of the solid, which is copper, 0.024 times the specific heat capacity of copper. We are given it to be 400. Theta 1 minus theta 3. That's 230 minus theta 3, which is what we are looking for. Okay. We move on to heat gained by the calorimeter. We've done this. Here it is. So we are moving on to heat gained by the calorimeter, which is this. And that's also MC theta 3 minus theta 2. So my M, mass of the calorimeter, is 0.06. Specific heat capacity is that of copper. We'll be making use of that of copper for the calorimeter, which is 400. Theta 3 minus theta 2. We don't know theta 3, but our theta 2 here is 31. So that is that for heat gained by calorimeter. Then I move on to heat gained by water. Which is equal to MC change in theta. The mass of water is 0.054. So I have 0.054 times the specific heat capacity of water from what I have here is 4,200. So I'm going to write 4,200. The change in theta is theta 3 minus theta 2. So now I'm going to solve everything together now. Heat loss by solid. If I simplify this, I'm going to have 24 theta 3 minus 744. Oh, sorry. So heat lost by the solid, if I multiply this by this, I'm going to have 9.6 into bracket 230 minus theta 3. Now for the calorimeter, if I go ahead and simplify this, I'm going to have 24 theta 3 minus 744. Then lastly for water, this multiplied by this will give me 226.803 minus 0.8 theta 3, minus 7031. So I'll just go back to this statement. The heat lost by the solid is 9.6 into bracket 230 minus theta 3 is equals to heat gained by calorimeter. Heat gained by calorimeter, which is 24 into bracket minus 744 plus heat gained by the water, which is 226.8 theta 3 minus 743. So if I go ahead to open this bracket, this is what I'll have. And that gives me theta 3 is equal to, I'll divide both sides, so I have divide both sides by this, and that will give me 38.34 degrees C. So my temperature, the final temperature, theta 3 is equal to 38.34 degrees C. Okay, so please don't forget to subscribe if this video has been helpful to you.